Look, our 14 minutes timer set. So that the 5 minutes time, so the 4 minutes time is compressed. So I've set a 40 minutes timer. The time now is 4:54 p.m. I'm announcing I'm 30 years old now. Well, I'm actually 24 years old, but my mental age is 30, so I'm 30 years old. So literally, and 25th of March 2026. The time now is 4:54 p.m. So let's go without further ado. Let's get to it. So much to do. Today I'm trying to learn. I've got my. I'm trying to do two things: robots and drones. Let me decide. Let me think. I have to decide. Either robot or drone. Should I basically I'm thinking what I should do. So I've got my sheet of paper here and I'm trying to model it properly. But it's not enough. So let me go and get the other piece of paper, the sheet of paper. I'll go here, set up sheet of paper. I'm gonna use it to work in this project. But it's all done. I'm trying to study calculus one, two, and three. I'm trying to learn rocket science today. So let me watch a video and watch because let me just see if I can get some notes here. So I can't find my book, possibly, my other books, my diary, my journal, my other one. But I have to buy another one. That's what that means. So I can't find it. But I'm keeping record on the big computer. Ontological Bayesian intelligence for Muco OS, Informatic, Kilo, Info Scott. We're building rockets and we're building rockets for drones, drone rockets, and we're gonna have drones. So let me just research what is already out there first. This is more of a research procedure. Uh, so um, so what is an orbit? Here, should I switch to this Coursera? Yeah. Let me start with this video here. Let me start with this video here. I'm kind of getting old, I'm getting old, yeah. So let me go and flip this video here. Let me just go and change this to 1 to scene 3. So this video is watching, and this video is here. It's orbit types introduction. Let's also choose.
Lo sai anche io, un po' di money means something, means something to survive. You get what I'm saying? I know. I see. Okay, yeah.
So basically, so since we're using models, but the problem, see, I see the models first, because the gravity of the height is different from the actual velocity. And I know she's going with this video, listening to this stuff. So So my next step is actually I'm really good at going to do, but I'm trying to have this system do something for me, and that thing is know when it's falling and know to check when it's falling. Basically, I have a mod of drift, and drift theorem basically is what the formula definition again or in the repository. So, this is basically one paper here describes the people, it does do the work, it does do the work. So, seriously, this is the drone model, one person kind of payload horizontally with it. So, again, we're drifting with the payload, but, the payload is a drone. So, I'm using rocket science to model the orbit of a system over the curvature. So you always moving over time. And so basically the altitude you get to the altitude that you get that you need to start gliding. So you don't have to point it closer. So you don't have to turn on the boosters anymore. And if I can make that if that altitude 15 obviously I don't know what the altitude is, but that's another altitude. It's not 0G, it's not that, it's something else. So let's go to the video. Yeah, that's cool. Um, so you have created orbits. You have let me just write this out properly because I haven't got a ruler or anything, but I just make believe I'm doing. So calculus 1, 2, and 3. It was a trident, there's many tripods for drone delivered network. So it has to be done properly because I'm doing the code, I'm the one doing it. So I'm the one programming the drones to do it. But I'm putting my own firmware into the drones. But if we just write the code, I'd be much happier than just write the code. But I've never done manufacturing before. So, let me not start with, let me just try to program the drones because I'm good at, I'm good at programming drones. And, if you respect this code, it'll be better than do that. So, the orbit types are elliptical orbit, and you have, so basically you get the elliptical orbit first. Oh, it's okay, that's the thing.
Okay, okay. Okay, so you're not person.
Okay, so this is all going in my head. It can't be writing down. So let's start this properly. We're gonna try and change the caption home. Which is have to get a bit of clean up to 65. So you're gonna have. So let me try to. Okay, so this will change settlers and orbits, and I'm choosing not to draw that we drop is the horizontal speed. I'm trying to interpret this properly. My system is knowing they're moving, knowing they're stopping, and we know what they're doing. But if you don't know what they're doing, know what they are, how can they know? How can I account for the system? So basically, I've got my work here. Basically, just pin this down. Just start this in the favorite section. Start it here. Start it here. Let me just add this to start. Yeah. So basically, I put it in STEM computing. Human code. Let me let this actually be a dashboard. I'm trying to have my website up and running again. One second. This is a deviation. This is my physics measurement. So this was the physics, but I'm trying to use orbits too. So let me get it straight. So it's the hydrogen photography, and let me write it down. So I go to people. Let me write it down now. Let me write it down. And so I got my paper here. So this will be trouble if I don't write it down now. But let's see what I can do to make it better. Um, so basically, let me try and model this one. So I'm trying to define a system of kind of like all my symbols. And I'm going to go my book to write my symbols by alpha, beta, gamma, theta, gamma, delta, epsilon, eta, zeta, omega, theta. Uh, um, yeah, that's remember. So that's remember. That's all that is. I don't remember. But let me try this. So I'm thinking of this Ziggy drone system as taking a kind of cargo and taking a payload into space. But I don't know how to put it as in a framework here. I know you have an elliptic orbit and you're gonna have an elliptic orbit. But when it comes down eventually. But yes, we've got that stage. So I had that with stage. So it's not there. So let me just focus on getting up to above the surface of the Earth. 100 meters kind of phase model view of the. So let's say we have two drones. They're doing colonization, but they are two drones that are drifting towards each other. So um let's say we have three drones. How many drones do we have? So I'm trying to now model how this will work computationally. So you have three drones. Three drones will fly to deliver aid to someone. So one delivers food. One does basically kind of a bird flight simulator. So one does deliver the food. One does the defending with the kind of information system using dimensional game theory and dimensional game theory, which are among pros and zero sum games, which are basically the style. And if you look has to develop a drone, food and shelter to someone that needs that's moving away because the world is naturally chaotic. So, we can understand that the fiction of pain is a grim reality where the drones are flying and they are going to be eventually shut down, but they're going to be computing ahead of time. So they're going to be, trying to compute something like, not compute something, like, welcome to come, visual observer, via drifter. So people that knows it's being a system in watch. So I can do this from myself. I don't draw a picture. Yeah, I have two pictures already. So this is what I did here. So this is my first one. This is what I did before, a long time ago. And this is the spring. And it's basically it has some K2 and the drone is carrying some weight and that thing can bring it up and down. So this thing have this. But speaking of the drone setting is I haven't done takeoff. So let me try to do drone takeoff. Drone takeoff horizontally or vertically, because if I take off horizontally, it can start to gain some that'll be 5 degrees angle. So let me try to model that quickly. Um, should I do drone rockets? One with the rocket. So let me try to do Human Wingman and Light Gunner, delivery drone. Hmm. I'm still thinking about the concept of the model, but the problem is the a lot of things gonna get weather, we're gonna get a lot of other things, other factors involved. But let's just work in the kind of the best case, just that the drone is not being attacked. I said it's been attacked before. Yes, I did say that. But let's work with this model. Let's work with this model here. We're gonna model. So 5 kg, 5,000 kilograms of food. Let's say 5 kg. Uh, 100 kg is a bag of rice. 100 kg is a bag of rice. A bag of rice. Let's make it 200 kg, 250 kg. A bag of rice. It's a bag of rice. 250 kg is a bag of rice. And the drone has to use its sprint to go up and down. So that means that for three of the drones. So let me try. Yeah. Let's just finish the video, watching the video first. Let's finish the video so I can get up. I feel so embarrassed. Serious stuff. So I've learned a lot from that, and I'm trying to do it properly now. So I'm come out here. So, it doesn't, it doesn't, I don't hate it, but I'm trying to follow along with the kind of thing I already know. I think I have to go to calculus one. Calculus one can show me how to do this properly. But, let me start writing something down. So, let me write some things down. So I'm gonna, follow kind of a vertical orbit. So basically, you have to go up to go higher. So basically, if you have to go up, do a loop, it comes down. But that was basically the start missile I made. And that's basically for we can put on a rocket, it will go like but it doesn't need to go. This is what, but if I have two drones, two guard drones or one drone, I can get myself through one shelter. Based on all that. But I'm moving away. So let me try and formalize it in language, in the way I know it. So gonna have let me see how people a rocket in orbit. Maybe a rocket in orbit stays in orbit uh, when the electrical when it's in a when the horizontal 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 vector component horizontal minus the let me see because I think it's so let me just try to find the system. Obviously, let me think. I can't remember. So, a ball falling down and a rocket, and rocket in orbit is the difference is the horizontal velocity, horizontal velocity, and velocity is usually moving in a direction, and that moving direction is like a integral derivative of space. The system has to be modeled in a way that is it's I'm taking one more taking off. I'm taking off a drone. But if I have a drone takeoff, my drone will basically fly straight up. It doesn't need to go straight up, but it needs to go straight up with a rocket. So let me try to do it because I'm trying to have a vertical takeoff. So let me try to write a V1 application for that. Should I? Okay, let me do it. So let me just start with pen to paper. So yeah, finish full charge. Rocket, I'll see these guys. It's my job. Rocket, I'm not stating with that because it has to be a rocket, an object, a rocket are stays in orbit such that because the horizontal vertical, a physical takeoff protocol. I'm not doing it because I'm not thinking too hard. I'm thinking too so. Let me start it. So Ziggy, Ziggy, vertical, 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 direct, take off, take off, vertical. So what does this mean? So the Ziggy vertical training pose the wind tracking model. And it's basically for via view for for basically vertical drift takeoff briefly via for drone delivery systems. Okay, so the drone Okay, so you're gonna basically I'm trying to have a vertical or vertical vertically, but usually to have a area covered. So the area basically being the what I see is on the ground. And when it starts to have an area, so let me try to do it via projected spline. So let me try to do it. So D1, D1, A, D1, drift D1, drift D1, or drift is angular shift, like redshift. Mm. Given shift D, given shift drift D is an angular shift given T of time. Mm. To, to drift to drift sequence and basically a drift the angular shift T T given time minus T given time is projected points. So projection P, like a vector position P in R3, in R3, in R3, such that T, such that um, minus TP minus PMC, DT, such that P minus C, such that T, such that C minus, such that drift an angular shift such position that it is a position P such that P minus C is P such as so basically a drift an angular shift such as in time T uh, time T such that such that T such that T um, such that P um, P minus C P and C such that T such that T minus C is the camera projection camera position. Okay, so just D T equals T T and C T. Just T where T is double is the magnitude of B squared minus 4AC um, beautiful vector injection model um, using using C is rectangular injection side. C is a camera position. So I don't know the data, but the output space is well. So you get a little curve, especially, and you get something good and something not good. So that's getting out of it. So you're gonna have so if I have first of it, if I have T is production supply, T is in change, or changing T is basically T as such that T is changing T. So that's my one. So the truth is an angular shift. So basically, you can now try to model when thrust is going to come in. If you have something that's coming through, this model applies, and this the spring force model. So that's what I'm saying. So this is coming to equation. So drones can, if I so basically 100 feet in air, you have to start going up somewhere. So this is what I'm saying. It's gonna have to measure something. This is a drone carrying weight, and this weight will be some kilograms of weight, and because it's a little bit. So let's find another video to do. So let me try to find this. So this is a 5 kgs carrying. Let's say it's 100 kilograms bag of rice. 100 kilograms bag of rice. 100 kilograms. And the drone weighs. The drone is 200 kilograms. Uh, if the drone is carrying, basically the food can fall at any time. So you have to slow down, speed up based on the what is observed. So get a minus cosine. So the model is that. So the first thing we will say, if I have ruler, let me just use it, guys. I'm Nigerian. This is only being in this one. And you have takeoff height. Drift off. So basically, so you're gonna have two lines, two left line. You're gonna have two left. You're gonna have D north to net 2 degrees. The angular shift of 90. So, for example, let's apply this formula here. So, a drift of this would be by time even so. Let's try to formula. I'm trying to get the problem down. So, if I can't solve this problem, I failed it. I failed what I'm doing, guys. Because I gave myself this one to solve, previously solve it. A drift, a drone carrying 100 kilograms of 100 grams, 100 1,000 1 kg of rice takes what vertically horizontally vertically uh, at 250 at 50 meters 50 meters uh, 50 meters for every 10 seconds. You say Um, 50 meters every 20 seconds. Calculate the drift of basically you have to do they have left and right drift. So calculate a drone carrying a liquid or bag of rice takes up or takes off vertically at 50 kilometers 50 meters for 20 seconds. 50 meters per second, 50 meters per second. 50 meters centimeters per second. That's kind of a very fast drone. But I don't think it's possible. Per second. I'm just getting started. Which I'm trying to use it. We don't need 20, we don't need them. It's a drone meter system. So 50 meters per second will be I'm trying to do from current to 1 kg, 1 kg. Let's just say 50 meters. Drone height is 50 meters per second. Determining when it is determining determining when what time the drone will reach orbital velocity given a electrical trajectory and b um, so they look basically the parabola. So basically, a drone carrying 100 grams of rice, 100 gram, one into one, so 1,000 meters, 100 grams, 100 grams of that rice. Let's make it 500 grams. 500 grams of that rice. Six of vertically. Uh, uh, how many miles is flying? Okay, let's say per second, 50 miles per hour, uh, per 50 meters, 50 minutes per hour, basically. I don't know, 150 meters per hour, 150 meters per hour. So you're gonna have the system work here. So I guess a question to solve this problem. And I don't really know due to this problem, but I'm not quite sure how the system works. So you're gonna have minus sign, minus cosine. Let's try to do it. So I didn't have to solve it. So I'm gonna try to do it. So position point or P determine geometry, two-thirds geometry, and half dimension. Uh, so I'm gonna try to find how to do vector projection again. I forgot. I forgot how to do vector projection. So vector projection, use of units, base units, the derivative units, common unit quantities. Student base units. Yeah, let me think about units first. I'm trying to find the video now for the system. But I'm gonna go a bit social for the six parts person. I'm not gonna use it, yeah, but it's gonna go up vertically, do a loop to loop, do a loop to curve and come down. So introduce, so these are all the stages. So I can do this. I'm gonna do well with it. So let me try and model what I was doing. For 2 minutes, so let me try and go. I failed already because you just come back later. So D given T, T is the training team is given by these kind of questions. So let's try to do it properly. Let's try this properly. Let's try this properly. In projection T is given 1 minus T, 2 third C times plus 1 third T, 2 third C times 1 third, that's 1 third in P. So the truth doesn't really matter, tremendously. So there's an area of the curve, looking like this area of the curve that dictates the division frame of the space here. So this is basically the space here. This is as it goes up, as the drone goes up, it has to lift the weight, and that lift is so the question is. Let me try to give it to AI. So let me try to a drone carries 1 kg of egg rice. To get off vertically 150 meters, 150, let's say 50 meters divided by 1 second. 150 meters per 150 meters per second. That's so there is no question. This is not physical question. So okay, 150 meters given can carry can at 15 meters for the drone carries 100 kg, 1,000 kg at 15 meters for every 2 seconds. For every let's say 15 meters. Basically, the formula here, the triangle formula here, V equals of velocity equals distance over time. So this on time. So V equals distance straight. Velocity equals distance with time. So that's how we'll stop. And I'll go for 5 minutes now. Can I go? So I'm trying to do it properly. So after pause this video, stop it now. So basically, I'm taking this formula, velocity equals over time, and apply it to the drift one and the quality for equation. We have to plug it into B squared minus 4AC. So there's no zero, zero interval. It doesn't mean a zero interval, but that's the vision done. That's it done. This is the next video. Yeah, so I'm going to continue video now. So this is velocity equals this over time. So I'm going to say this because it seems more like a solution and problem here. So for drone, 1,000 kg, carrying 1,000 kg, a bag of rice. I don't even know the drone weight. Let's say the drone weight. Let's say you have work. Work equals power of efficiency. Energy times power. Power. What is it? work, work equals power times time. Work in physics. Work in physics. Um, power and time. Work power and efficiency. So these are important. Work is space times displacement. 20 joules of work. Work times displacement. Work equals force times distance. Force times distance. Work is measured in joules, force measured in newtons, and this motion summation of meters measured in meters. So, okay, so what's the physics of the system? So my drone is flying. Um, Basically, it's a bag of spring. It's falling up and down. So it's characteristic. So basically, it's spring. It's powering a drone carrying 500 kg, 1,000. But my drone could be smaller. I also call it foundation. I didn't know to say that. It's brown very well. The drone carrying 500 grams of rice at 15 meters, 15 and takes off 15 minutes. Has a terminal facility. Takes off at a terminal facility or 15 um, of the of 10 meters. 50, I'm just trying to find drone flights examples, but I don't think it's gonna work. How fast is a drone take off? Fast or drone, yes, drone speed, drone speed, uh, drone 25 miles per hour. So, 25. Uh, um, so for 5 miles per hour, and basically, we have a running car. So let me try to go because I'm trying to work it together. Something common something. So the weight of the drone is difficult to do. So I'm trying to take a drift demon. So models is a system of tripod stick. I'm trying to do it properly. So let's do it properly. So you're gonna have with formulas, fundamental formulas. Here first, let me do that properly. So you're gonna have dt equals pt minus ct. Um, where where changing t equals t surely time equals w squared d squared minus 4ac. Um, equals projection. Um, Position p is a position. Position. Um, let's see. Position. Distribution. C is a canyon. So basically, he and C, and C are there. So you're gonna have basically have 2 points. W, which is WT, the weighted average of a point is weighted average 1 minus T times C times T times P. I'm gonna have the flip, this is the algebraic AW. I'm gonna have GW, which is geometry, which is T dot P plus 1 dot C. You have the two formulas here. You're gonna have the racial equations. You're gonna have because the probability decay, y equals x equals plus or minus square root of b squared minus 4ac 0 to so you can have the little curve there, the little curve. So you can have three formulas here. So I have three formulas here. So let me do I'm gonna have work. So work equals the force times distance. Work equals force times distance. So you're gonna have velocity distance velocity velocity equals to um, distance over time, one by time. And the velocity of a system is a time. So you're gonna have two sets of equations there. So we will try to model them. So we just do this. So my jewel is carrying something that will pulling it down. So what this means is that my jewel being pulled down by weight. And that weight is like my jewel is so drone speeds are so the thing is with a drone carries, but I don't know how much a drone weighs. A drone weights because I'm being a drone now. Drone weight is under drone weight. Drone weight. So the weight. So I'm trying to drone weight is consumer drone. So let's say 100 kilos. Consumer drone is 1,200 to 1,300 grams. 100 kilos, 6 kilos, 6,000 grams. So, okay, a consumer drone. So let me use the answer. My drone is a drone. I'm the right answer. So I'm gonna eat after this, but I'm trying to want to set it from here. Let me write my first. So a drone, or for a drone, from a drone, uh, with mass of 250 grams uh, carries vertically uh, a bag of rice, uh, 100 grams. It's it's what do you know? It's vertical takeoff is so 5 miles per hour. Let's say It's terminal. It's terminal. Takeoff is 125 miles per hour. Let's say it's 5 miles per hour. Yes, that's right. So it's terminal takeoff is 5 miles per hour. A drone delivery with the mass 250 grams carries a physical battery physically. A physical takeoff is 25 miles per hour. Calculate, determine determine what the vertical determine sequence. Okay, determine two things. Determine when the drone uh, has is what speed interval the drone reaches an elliptical curve. Like see, I never know. I'd love to go back in country now, just to start a PhD there. But these people are giving problems. So, something what's happening to the drone, which is an energy curve, um, and arrives the this energy curve arrives at Spruance using the truth theory. So, so arrive also is the when the projection D uh, given D T minus T T minus C T. And B, basically when it's in orbit, when it's this is the third order of control with the curvature in orbit via the second order, second order, the curvature of the space, in the case of the and when it arrives in orbit. So I'm trying to do this properly, but it has to be done correctly. So I'm gonna eat now, but I've done the work. So so the drone delivered the mass 250 grams. The bag arrives of 100 kg takes off for 5 miles per hour, has a terminal velocity of 5 miles per hour, and determine when the drone at any interval at with initial velocity of 25 miles per hour. Basically, 25 has a 25 miles per hour elliptical curve. A mass of basically a drift theorem, a dt, which is the drift given t, the time velocity t, or changing t equals to double magnitude t, or changing t given t such that changing t is double magnitude of the d squared minus 4ac. which is a time, actually time interval. You can find the time slice, in orbit, has a residual. So they have utility and trying to model. And utility are basically, like, going up, uh, curvature and control and collapse. So you get the full integration. But I'm trying to trace two single questions. So trace the derivatives to verify the elliptic curve trajectory, 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 trajectory is a non-zero vector. Is a non-zero vector at each interval. In orbit, and then coming down control collapse, control to collapse. So no, basically, I think this is gonna work. But I'm gonna upload the audio clip here. So let's just see how this works. So this is gonna be an MP4 video. So the problem is this. So the timing, a drone, the mass 250 kg, carries a vertical bag of rice, 100 kg. It's vertically take off 25 miles to 55 miles per hour. 25 miles minimum takeoff velocity. It's determined when the drone at one interval will be curve. The mass of the mass at orbital, the drone theorem, basically the first is basically the oscillation, basically determine when the drone what the when the drone at what interval analytic curve, using analytic curve. Basically, when it goes up and down, using determining what time, using given a drift theorem. So, basically a drift of an angular drift, basically, you're gonna be kind of this. You're gonna have a left, a right, and an up, based on tripolar color coding, and the color coding determines the time of the interval. So you're gonna have three color codes. So the position of the point of P is what the camera is watching when it goes up, and this drone is going up this way, and by going up, it's flying high, and by flying high, it's doing a long up, and that long up basically produces this space and time here and here. So uh, in orbit, so and to show that derivative orbit derivative is derivative the elliptic trajectory there's a non-zero vector at each interval. So basically, the non-zero vector is a non-zero horizontal or non-zero horizontal vector. Horizontal, basically, it's sustainable and it can fly in the air. Basically, it can, with enough fuel, it can keep afloat in the air. This is what I do for the second question. Let me try and solve the jump and eat my lunch. So let's do this. Seeking normal system. Years six feedback loop with so that's go to video.